Welcome again. Today we'll have a look at an FRQ from 2015 about differential equations. On this FRQ, students did quite poorly with a mean of 2.67 out of 9. It was the lowest score of all AP FRQ questions in 2015. 15% of all students earned no points. There are other FRQs where there's a larger percentage of students who earned no points, but here, overall, the score was the weakest. So there's questions A, B, C, D. We'll jump right in with question A. Consider the differential equation dy dx equals 2x minus y on the axis provided. Sketch a slope field for the given differential equation at the 6 points indicated. You are given this, it's repeated, it's in the question, but it's also repeated on the answer sheet, so you don't have to worry. You'll have this system of axis with the 6 points. Here's what student A did, and that's perfect. There were 2 points. I'll talk a little bit more about the points, but in this FRQ, the points were given 1 point if these 3 answers were correct, and 1 point if these 3 ticks were correct. So how can you evaluate, how do the evaluators judge whether it's correct? It's hard to determine, but what they focus on is slopes of 0, it has to be horizontal, slopes of 1, and slopes of -1. And after that, they compare slopes. So at the point 0, 2 here, if we look for the slope, dy dx, the slope is 2 times the x value minus the y value. So at the point 0, 2, the slope is 0 minus 2, -2. This slope is -1, this slope is -2. They're going to compare and check that the slope here is steeper than the slope there. Likewise, at this point down here, the slope is 2 minus -1, so the slope is 3. They're going to compare it with the slope here. The slope here is 0 minus -1, which is 1. So that slope is 1, that slope is 3. We don't know exactly what the slope of 3 looks like, but you have to make a tick that is steeper than here. So they look at slopes of 0, -1, and 1, and then they compare slopes if they are larger. Our second student wrote the slopes next to each point. It's not necessary, but it can help, and they earned 2 points as well. The third student created a little table with x and y values and then made the ticks correctly again, and also earned 2 points. Question B. Find d square y dx squared in terms of x and y. This is the second derivative. We are given the first derivative, so we just have to differentiate this again. This is implicit differentiation. And then determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. This student does a really good job. His work is super neat. Let's see what they did. First they repeated the dy dx, and then when you differentiate this, the derivative of 2x is 2, the derivative of -y is -y prime, written like that. This is good, but if you look at the question, it says specifically that you need to give your answer in terms of x and y. So you are not allowed to leave some y prime in your answer. To do that, you can substitute y prime with 2x minus y, because y prime is equal to 2x minus y. So the final answer is here. Then the student rewrote the answer and boxed it, and that was correct. 1 point. For the second part of the question, determine the concavity of all solution curves in quadrant 2. Quadrant 2 is the top left part of the Cartesian plane. X is less than 0, y is greater than 0, so if you go over these three terms. This is positive, of course. This is positive as well because x is negative, and this is positive. So overall, the second derivative is going to be positive. That means that all solution curves in quadrant 2 are concave up. Good job. They find the right answer, and the explanation, the reason, is clear. The second student found the second derivative, so that this here's the derivative of 2x minus y, and then they also substituted y prime with 2x minus y, so this is correct. And then quadrant 1, quadrant 2, quadrant 3, quadrant 4, they substituted. This, I guess, means x is negative, y is positive. This means x is negative, y is negative, and so on. So they correctly concluded that the second derivative is going to be greater than 0. And finally, the explanation is the concavity in quadrant 2 is always concave up. Well, I guess the explanation is here. So 2 points as well for student B. Student C found the second derivative, 2 minus y prime, and then started something a little bit bizarre, set up the second derivative equals 0, which, why would you do that? Probably when you're looking for points of inflection, because points of inflection happen when the second derivative changes sign. This can happen when the second derivative goes through 0, or it could also happen if there's like a sharp turn or something. So setting this up to equal to 0 was not the right idea. At this point here, the student hasn't yet substituted y prime, but they do it a little bit later here, 2 minus y prime. So the evaluators from AP Central gave that student 1 point for that, but nothing else makes sense in this solution. But just be aware that even here the point was given, but it's not the correct answer. It should say d squared y dx squared equals this. Question C, this is when it becomes much harder, but I like this question a lot. It addresses a problem that I've seen very often in my classes. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? Justify your answer. Student 1, student A, does it correctly. They first look at the first derivative, because if you have a relative minimum or a relative maximum, your first derivative needs to be 0 or undefined. In this case, if you substitute x equals 2 and y equals 3, this is given here, x equals 2, y equals 3, you find that the slope at the point is 1. So how is it ever going to be a minimum or a maximum? Definitely never. So that's all there was to do. When you see that the slope at that point is 1, you can conclude that it's neither a minimum nor a maximum. That seems easy when we see the correct answer, but let's look at student B, because they did exactly what you could expect many students to do, so it's interesting. They thought, given, according to the second derivative test, at the point x equals 2, the second derivative is positive, therefore there is a minimum at that point. That earned 0 points, and we'll see why. By the way, it's true that the second derivative is greater than 0, but if you apply the second derivative test like this student does, you must first check that the first derivative is 0. This is the correct solution curve for this differential equation, and it goes through the point 2, 3 here, so that's the correct graph. If you had the graph, of course, the question would be easy. It's neither a minimum nor a maximum, but however, it's very hard to find this graph. We actually don't study the methods in AP Calculus AB to find this. If you only study the concavity, you will correctly find that the graph is concave up at this point. It turns left. But as you see, the first derivative is not zero. So when you apply the second derivative test, you first need to find a point where the slope is zero. When the slope is zero, like this, then you can look at the concavity and you will conclude correctly. If the concavity is up, then it's a minimum. If the concavity is down, then it's a maximum. But don't burn the first step of the second derivative test. The third student tried to separate variables. So because we have a minus y here, they added y on both sides, and there's a little mistake, but we see the intention here. The intention was to separate the variable and then integrate, and who knows what's from there. This doesn't work, because when you separate the variables, you need an expression in x multiplying dx, and you need an expression in y multiplying dy, which is not the case here. This plus y is not multiplying this dy, it's added to dy, so it doesn't work, and the student didn't earn any point. In fact, as I just said, it was not possible, given what we know from AP Calculus AB, to find the solution to this differential equation. If we try to separate the variable in a case like this, dy dx equals 2x minus y, we can try to do what student C did, adding y on both sides, and this is where we get. And from here, maybe we want to try to multiply by dx, so that we would have 2x dx. This is what we find. However, we have another issue now. We have the y dx here, which we don't like, so what shall we do? Maybe we'll try dividing by y to get rid of that. And after we do that, we're happy with this part, 1 over y times dy. We're quite happy with this dx, but now we've moved the problem somewhere else. We have a y here with dx. So when you do that, you can try. It's not unreasonable to try, but after a while you have to accept that it doesn't work. And if it doesn't work, then it means the solution is elsewhere. So student C kind of probably realized it didn't work, but didn't want to accept it and just went through and hoped to get a point somewhere, but they didn't get it. So we don't know in AP Calculus AB how to solve every type of differential equation. We just really know very few methods. We know only how to separate variables, and if you can't, then you can't solve the problem. In question D, this was a very hard question. The question asks, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. When we see that, again, solution to the differential equation, the first thing we would think of would be to try and solve this, but I just said it, we can't. We can't separate the variables. So there must be another way. If this is a solution to the differential equation, then we can take the derivative of that, and it should match this, because this is the derivative of all solutions. So taking the derivative of that, we find that dy dx equals m. It's written here, dy dx equals m. That was 1 point already. If you went a step further and said that the derivative m has to be equal to the derivative 2x minus y, which is written here, then you earn the second point. After that, the student went through and substituted y equals mx plus b, so you get m equals 2x minus mx plus b, and the student then put the x's together, so put the like terms together, m equals 2 minus m times x minus b. What can we do from here? Equate coefficients. The student is obviously really strong. What does he mean, or what does she mean by equate coefficients? If you look at this line here, m actually means 0x plus m. And then on the other side you have 2mx minus b. So we need this to be true whatever x is. We can choose x equals 1, we can choose x equals 2, we can choose x equals 57. It has to be true all the time. So That means that the coefficient for x has to be equal on both sides, so that whatever x is chosen, it'll always match. And then the constant has to be the same on both sides as well. So if you look at what's in purple here, 0 has to be equal to 2 minus m, and m has to be equals to negative b. The student does that, 0 equals 2 minus m, and finds m equals 2. And then the student sets up m equals minus b and finds that b is negative 2. So going through this long technical process earned the third point in question D. This is really something we don't practice. It's extremely rare. It was kind of a challenging question that goes beyond the expectations. So kudos to all students who found the answer. Student B got 2 points actually in this exercise extremely rapidly. First of all, they recognize that if this is a solution, then the derivative of this line is m, and that it has to be equal to the derivative of all solutions. So they wrote m equals 2x minus y, and that was the correct answer. After that, they couldn't go further, but 2 points out of 3 in this question is very, very good. Student C insisted a little bit further in trying to solve the equation, and it just doesn't work. You can't, well, there's an integral here, and then this becomes the derivative, so we won't talk about this too much. There's nothing to learn about this solution here. So some common mistakes. Most students presented a lot of work in all parts of the problem. Many students were unable to work with this non-separable differential equation. In part A, for those students who sketched incorrect segments, the most common errors were at the point 0, negative 1 or 1, negative 1. This comes from the fact that the differential equation was 2x minus y, so I guess it became 2x plus 1. Some students sketched a vertical segment at the point 1, 2 instead of a horizontal segment. Yeah, if the slope is 0, that's horizontal. Some students simply left part A blank. In part B, many students did not recognize Leibniz notation for the second derivative. This is what they mean, Leibniz notation dy dx and d square y dx squared. Some students were unable to provide a complete reason for the conclusion, and then most students did not answer part D correctly. Some students attempted to solve the differential equation here also, just like student C. Most students believed this part was an extension of part C and found an equation of a tangent line at the point 2, 3. Recommendations. Slope fields have been tested regularly on the AP Calculus exams, and students should be able to create a portion of a slope field for a differential equation. Although students are not expected to solve a non-separable differential equation, they are expected to be able to obtain information from and work with any differential equation. Teachers should emphasize to students that the behavior of a particular solution and properties of the family of solutions can be obtained from the differential equation without actually solving the differential equation. In addition, teachers should use various notations for the derivative, including Leibniz notation. So let's review Leibniz notation. This is y prime if you write dy dx, and the advantage of writing it like that, well, there's two advantages. First of all, you know what the variable of differentiation is. If we had something in terms of t, then you can write dy dt. If it's in terms of s, then you can write dy ds. The second advantage is that if your function is not called y, but if your function is called something much more complex, you can still use d dx and then express the function. This is an example we saw. We can't write dy dx here because this whole thing is actually an integral, so we can use Leibniz notation to write this. When you go to the second derivative, this is the way you write it, d squared y dx squared. Why do you have a square here on the d and a square here on the x? I don't really know. I can't explain that. But definitely, if you want to write something similar to here, then it's going to be really useful that the square is on the d, because you still want to know that this is a second derivative. So the square appears here, and the function, it's not the function squared. So we have to be, it's better that the square is with the d. Thank you very much. I hoped this helped, and good luck in your study for the exam.